Hi everyone. In this short video I'm going to give you the solutions to the first part of the diagnostic quiz. So this is just the probability questions. Question 1 asks us, a fair coin is flipped 10 times. Compute the probability to see 7 heads. 7, and this is exactly 7 heads out of 10 flips of a fair coin. Okay, so let's parse this. There are 10 slots. Six, 7, 8, 9, 10. And any one of these sequences, heads, tails, heads, whatever it is, has probability 2 to the minus 10. Now I will be happy if 7 of these 10 are heads, and that can happen in exactly 10 choose 7 ways. So I need exactly 7 out of 10 flips to be heads. And this can happen in 10 choose 7 ways, which recall this is equal to 10 factorial over 7 factorial and 10 minus 7 factorial, which is 3 factorial. And therefore, the total probability that I'm looking for is the probability of each one of these 10 factorial over 7 factorial, 3 factorial, the sum of these. So the answer is 10 choose 7 times the probability of any one of these particular sequences. And this is something like 0.11719, 8, etc. So this is the first question. And again, the two keys, the first one was counting the number of good sequences, good meaning that satisfy the property I want, having exactly 7 heads. And the second was computing the probability of any given sequence. So let's actually belabor this point a little bit and explain how we got the probability of any given sequence, because we will need that next. So what is the probability of, let's say we just flip the coin 3 times, so I don't have to write out 10 different outcomes. So let's compute what's the probability of a fair coin of heads, tails. Well, these flips are independent, so it's the probability of heads on the first times probability of heads on the second times probability of tails. Since it's a fair coin, this is just 1/2 times 1/2 times 1/2, or 1/8. And this is how I got my 2 to the minus 10 up above. Okay, so this is directly relevant to the next question, so let's move on to that. This next question is a little bit more tricky. So the next question says, what is the most likely sequence if we flip a coin that has probability 2/3 of being heads? So this is a non-fair coin that has probability of heads equal to 2/3, and of course this means probability of tails is equal to 1/3. So let's compute the sequence that we saw above. Okay, and this will warm us up to get us up to the question of what's the most likely sequence. So with this coin, if I repeat my calculation, probability of heads, tails, again because of independence, is the probability of heads times the probability of heads times the probability of tails. Okay, so let me note this is because this equality is because flips are independent. What that means is whatever I got on the first flip doesn't influence what I expect to get on the second one. if you're flipping a coin, whether it's fair or not, and you've seen a run of 5 heads, though it's tempting to believe in this concept that there's such thing as a lucky day, in reality, or in the reality of probability, that's just not the case. So whatever it is that you got yesterday, whatever it was that you flipped in your last 10 flips, what you're going to flip tomorrow is exactly going to be according to the probabilities. In this case, 2/3 and 1/3. So this is equal to 2/3 times 2/3 times 1/3. Okay, whatever this is. So this is, what is that? 4 over 3 cubed, which is 27. Okay, so now let's go on to this question and ask, what is the most likely sequence? Okay, it doesn't ask how many heads do you expect to get or how many tails do you expect to get. It's asking what is the most likely sequence. So the first choice is, in fact, the correct answer, which is that the most likely sequence is heads, 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 heads 100 times. Heads, 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 heads 100 times. Okay, so why is this the correct solution? It seems a little bit confusing. Well, perhaps there's another solution. Perhaps there was a tails in there. Let's compute this probability of this sequence, which in fact will be the solution to the next problem. So probability of heads, heads, blah blah blah, heads 100 times, again because of independence, is equal to the probability of heads times probability of heads times etc. 100 times probability of heads, which is equal to 2/3 times 2/3 times 2/3 all the way to the end. So you see, if you think that one of these, that there's something else that's the most likely sequence, we see right away that that couldn't be, because any other sequence would have to have a tails, and I would just be swapping a 2/3 for a 1/3, which would only make this product smaller. Okay, so the answer is to this question is 100 heads. Now let's actually compute what is this probability. So this is, now we're on to question 3. We've basically done it. So this, the probability of the most likely sequence, i.e. the probability of 100 heads, is just what we wrote here. 2/3 times 2/3 100 times, or 2/3 raised to the 100. This, in fact, is much, much less than 1 in a million. So in fact, it's about something like 2.45 times 10 to the minus 18. So it's much less than 1 in a million, much less than 1 in a billion, much less than 1 in a trillion. Next question is, now the next sequence of questions focuses on asking us to compute marginal and conditional probabilities given joint probabilities. Okay, so what does it mean? We're given this table here. Coin 1 equals heads, coin 1 equals tails, coin 2 equals heads, coin 2 equals tails, 1/4, 1/4, 1/6, 1/3. So what does this table mean? It's telling us that the probability that coin 1 equals heads and coin 2 equals heads equals what's in this box? 1/4. Now this is also what we would expect if we flipped 2 independent fair coins. But to convince ourselves that they're not independent, okay, let's compute the marginal probabilities. And in fact, this is exactly what this question is asking us to do. And so this question is asking us to compute the expected number of heads if we flip the first coin 100 times. So to compute the expected number of heads if we flip coin 1 100 times, what's the key thing we need? Well, actually, just write down the answer. So the answer, this is just going to be 100 times the probability that coin 1 is equal to heads. Okay, but you can see that this is not directly given. So we must compute this. If you recall from your probability, this is called the marginal probability. Probability of coin 1, okay? As opposed to the joint probability of coins 1 and 2. So we need to compute this this marginal probability. So let's do that. I'm going to scroll up a little bit. We'll have to, actually I won't scroll up so we can see these numbers. So the probability that coin 1 is equal to heads, I have to somehow get this information out of this joint. So when does coin 1 equal heads? Well, it's equal to heads when coin 1 is equal to heads and coin 2 is equal to heads, and also when coin 1 is equal to heads and coin 2 is equal to tails. So now we're in business because these two numbers are specified in our table. And looking up above, I see that this is 1/4 plus 1/4. So this is 1/2. Just for exercise here, let's also compute, even though the problem doesn't ask. Okay, but just to complete the solution, so we see that the solution is now the first choice, which is 50. Okay, so we can now go in and fill in this the answer here. This is equal to 50 because it's 100 times 1/2. But now let's just for fun, let's compute the marginal of coin 2. Let's see if I can. We'll have to do a little bit of scrolling, or perhaps not. So the probability that coin 2 is equal to heads is the same kind of calculation. It's the probability that coin 1 equals heads, coin 2 equals heads, plus the probability, not that coin 1 equals head and coin 2 equals tails, that's not what I care about. I only care about coin 2 right now being heads. So it's this. And this value now is basically the sum of the elements in the first column, not the first row. So this is 1/4 plus 1/6. And 1/4 plus 1/6 is equal to 1/3. Is that right? Let's see. 3/12 plus 5/12. Nope. Made a mistake. Let me do it more slowly here. It's 3/12 plus 2/12, which is 5/12. Great. So now let's, another side thing that this question doesn't ask, but let's just convince ourselves that these coins are not in fact independent. So the probability that coin 1 equals tails is 1 minus the probability that it's equal to heads. So it is equal to 1/2. The probability that coin 2 is equal to tails is equal to 1 minus the probability that it is equal to heads. So it is 1 minus 5/12, or 7/12. So what about now the probability that coin 1 equals tails and coin 2 equals tails? Well, we don't have to, we can just look at this table. So scrolling up a little bit, we see that it is equal to 1/3. And it's this value right here. So we know that this is 1/3. But note that this is not equal to the product. So the probability that C1 is equal to tails times the probability that C2 is equal to tails is equal to 1/2 times 7 over 12, which is equal to 7 over 24, which is not equal to 1/3, and which is different from 1/3, which in fact would be 8 over 24. Okay? So you see that this shows that these coins are not independent. It's hard to imagine a world where two coins aren't independent. It basically means if one coin has already come up tails, that influences the probability that the other coin will come up heads or tails. But this is just a probability example. So this shows that in fact that these coins are not independent. Now this is all sort of supplementary to the diagnostic quiz. So to remember where we are, question 4 asked, what is the expected number of heads if we flip coin 1 100 times? This was 100 times this marginal, that probability of coin 1 equals heads, and this is what we needed to compute. Okay, so we did that. Let's go on to the next question, question 5. Question 5, I'm going to copy this table so I don't have to keep scrolling up and down. So this table again is 1/4, 1/4, 1/6, 1/3, coin 2 equals heads, coin 2 equals tails, coin 1 equals heads, coin 2 equals tails. And this problem says that it assigns a score. So what we're essentially doing is saying that heads has value 1, tails has value 0. So the score is equal to 1 if heads, 0 if tails. Okay, so it'll allow us to do some numerical computations. So it asks us, the question here is, what is the expectation of the score of the second coin conditioned on coin 1 coming up heads? So this is basically asking, so this is equal to, the score is equal to 1 if the second coin comes up heads. So this is equal to 1 times the probability that coin 2 is equal to heads conditioned on coin 1 being equal to heads. And the score is 0 if the second coin comes up tails. Note, we're always conditioning on the same event because this is the question. You're conditioning, we're now living in the universe where coin 1 came up heads and we're about to flip coin 2 and we're asking, what is the expected score? In other words, you can see what's really asking is, what is the probability that I'm going to get heads with the second coin conditioned on the fact that I got a heads on the first coin? So now what this question is really asking us, the probability concept here is that of conditional probability. Conditional probability. And in order to do this calculation, the formula that you need to remember is that the conditional probability is defined as follows. The probability of coin 2 equal heads, condition on coin 1 equal heads. Notice this is not given, so just like with marginal, we need to derive this. This is equal to the probability of the joint. So probability of coin 2 equals heads and coin 1 equal heads divided by the probability that coin 1 equals heads. So this top value is given. It's the upper left element of our table, 1/4. And the bottom value we computed in exercise 3. We computed this to be 1/2. So this value is 1/2. 1/4 divided by 1/2 is 1/2. And therefore the answer is 0.5. So let me write out why the answer is 0.5. So now we can plug this in to our expression. So what I'm going to do is now I can write out what this is. So it's equal to 1 times this thing that I just computed, 1/2, plus 0 times, well, it doesn't really matter what the rest of it is. We know that, in fact, it'll still be 1/2, but it doesn't even matter because it's times 0. So the answer is 1/2, or 0.5, which is the first choice in the diagnostic quiz. Okay, so now the next question is asking us to remember what the definition of variance is. Question 6 is asking us to compute the variance of the score of coin 2 conditioned on the event that coin 1 is equal to heads. Okay, so what we need to recall here is that the variance of a random variable x is defined, this is a symbol for definition, is defined as the expected value of x minus the expected value of x squared. Okay, so intuitively what this is trying to measure is how far away are you from your average. The more variance you have, the more you expect a random variable not to behave in a similar way at every flip. If you have 0 variance, it means that every time you're very dependable, you say the exact same thing. If you have huge variance, it means you're very, very far away from what you do on average. And with just some basic calculations, you can compute that this is sometimes useful for, makes it easier to compute. This is equal to the expected value of x squared minus the expected value of x, this whole quantity squared. Very important to remember that these two are different. The expected value of x squared is different from the expected value of x, quantity squared. Let's apply this to what we want. So we have already computed. Okay, so in our case, we want to compute. So for this problem, we are asked for the variance of the score of C2, that's our random variable, conditioned on the event that C1 equals heads. So applying this formula, we want to compute the expected value of the score squared of C2, conditioned on C1 equals H, minus the expected value of the score of C2, conditioned on C1 equals heads, all of this squared. So now we're happy because we've actually already computed this in the previous exercise. So we know this inner thing is 1/2, so therefore this value here is 1/2 squared. Okay, so what about, so we still need to compute this over here. Expected value of the score squared of C2 given C1 equals H. Well, let's think back to how expected value works, it's the value times the probability of that event. All of those summed up. Now the score is just 0 or 1, so actually the square is not making our life any harder. And so this first part is equal to 1 squared, or just 1, times the probability that C2 is equal to heads, condition on C1 equals heads, plus 0 squared times the probability that C2 is equal to tails, condition on C1 is equal to heads. So, in fact, all we need, this is just equal to this, which we also computed in the last exercise. So putting it all together, so from this value here, recall we just computed above, is equal to 1/2. I'm going to scroll up so we can remember where it is that we computed that. It's right here. Probability of C2 equals heads. Condition on C1 equals heads is equal to 1/2. I'm going to erase these lines so they don't make a mess when you look at the record. Okay, so scrolling back down, I can now fill this out. So we now have what we need. So this equation now reads, the variance of the score of C2, condition on C1 equals heads, is equal to 1 squared times 1/2 minus 1/2 squared, or 1/2 minus 1/4, or 1/4, which is answer number 1. This is the end of the first part of the diagnostic quiz, which had probability questions. You can check the next video for the second part of the diagnostic quiz.